go. So welcome back officially. Happy Tuesday after break. We are in the home stretch of the semester. We're finally allowed to start the countdown. Spring break is the official marker of when we can start counting how many more classes and how many more things have to get done over the next month or so. But one of those things, homework 4 here, we had some questions over. So I have it pulled up, and let me know, Mary, which ones you want to talk about.
So, question 20 and 21
Okay.
are about the change in proportion. Um, and all of the other numbers I've gotten correct.
Okay.
I just for some reason can't figure out the change in proportion of explained variance and the test statistic for the change. Both of those numbers are coming up wonky for me.
Okay.
Is there something I'm doing wrong for the rest of the numbers to be good and those to just not be right? Or,
Not necessarily. Can you describe your process that you've used so far for finding those values?
oh gosh, yeah, I did that yesterday. Let me get my brain right.
Fair enough.
Okay, so that is section. So I actually figured out that if I divide it off into sections, like you do through where you put the hashtags and all of that, then it makes it easier for me to go back and look at things. So that
Yes.
is
Yes, and I
four.
would also recommend answering the questions about the numbers as you fill in the numbers. That way you're 100% certain which model you're talking about because they do
Yep.
change. Yep.
Okay, so for that one, I did the LM. Does that make sense?
So LM is the function that will give you the model.
Right.
And then LM summary is the function that spits out the results and effect sizes.
Yes. So for section 3, why can I not find that? How I divided it off into sections. Oh, never mind. I have the wrong thing open. Hold on.
Fair enough.
Stupid console was open. It wasn't in the. Okay, so section 3, we did by rating.
Mm-hmm.
And then I did motivation 4, because I'd centered that, verbal 500 plus quant 550.
Mm-hmm.
And then I did the summary.
Okay. So then you have, it looks like the results for that new model in
Right,
terms of like what that current model is telling you about the prediction.
right.
Okay, so then 20 and 21 is a separate command because you're
Ah,
asking about how the models compare to each other.
okay.
If that hint hint.
I knew I was forgetting something. I was like, there's got to be a step that I'm not seeing.
Yeah, and we can talk about that today too in more detail if that's needed. But yes, anytime you're
Okay.
adding multiple things to a model to get the assessment of how much the R square increased and the corresponding F test for the multiple things, that's a separate step.
Okay, perfect. Then that's where my brain has kind of gone. So I had
Okay,
it on my list of things to do to ask about that tonight, but also to rewatch the example video. So
cool. All right. Do you have other questions or is that the one that you're on for right now?
no, that it's those two, and then the section 4 is kind of the same where it's comparing the models.
Yep, yep, it'll be
It's
the
the
same
same
process
question.
for both. Yep,
Yep.
yep, yep.
Yeah, but everything else is green. Yay!
Yay! Congratulations. And for those of you who might be a little panicked, like, wait, were we supposed to do that? Not yet. I just put stuff up early because I know y'all are working on different schedules with your jobs and your lives, and this is conference travel season and other kinds of things that are happening. So I wanted folks to be able to get started as soon as they humanly wanted to on these things. The next thing is actually just your project plan documents if you have not sent me that already. I've been looking through them as they've been coming in, so I've got a few folks already registered for that. But homework 4 is due the week after. So let's look at the schedule just to make sure we're all literally on the same page here. So
Oh,
today go
I'm
ahead.
sorry, but we were supposed to submit something for the project this week?
Not this week. It's due next
Okay.
week.
Yeah. Yeah.
Yep. Yeah. No, a few people already did so, and I read those plans and have corresponded with them. So if you want to get it done before Sunday and you'd like feedback sooner, just let me know. I've been trying to get them back to folks as soon as possible. Cool. Yes. So today was formative assessment number 5, which we're going to talk about, and then we have. Let's see. What's too far here? There we go. We have the project plan due next week. Homework 4 that we were just talking about is due the week following. And then we have 2 formative assessments and then the report. So finals week will consist of finishing homework 5 if you haven't finished that already, and revising your project if you feel like you want to do so. That's optional. What I will give you is detailed feedback in comment bubbles in Word, and I would ask you to go through basically the same process as if this were a manuscript or a grant. You respond to the feedback in the document, you make your changes. You can, have a conversation with me in the comments if needed about things or whatever, and then I look at what I asked you to do, if you fixed it, and then I give you your points back. If you get your report back and you're like, yeah, this is good enough for me, I've got other fish to fry, I don't need to spend more time on this, I'm fine with that. I'm a very pragmatic person when it comes to making sure that all the balls in the air drop or don't drop according to however it's needed. In terms of when the reports are coming back, as soon as humanly possible is my intent. Like, I'm just going to sit down and read them the next day and hopefully get through all of them, because there's only 12 of you at this point, so that's a fairly manageable task. That way you'll have as much time as possible to put that together. And as I mentioned at the start of class, a couple hours ago, I posted the instructions and rubric for that in terms of what I expect. I tried to make it general enough to fit everyone's situation, but if you're not sure what to do or what to report, or if you have multiple options in terms of what you do and you want me to weigh in, please let me know. Even if you've already submitted your plan, we can continue dialoguing about that as needed. All right. What else? What am I forgetting? Nothing? We're good? Okay, well, I'm going to consider that a win coming off of a break, trying to remember where things are happening. Then how about we chat briefly about formative assessment number 5? Will that work for folks? Okay, so folks are liking the immediate feedback and getting the chance to fix your answers, so we're just going to stick with that. If you want to go through this multiple times and change your answers, go right ahead. But I think it's also important to realize why the answers were correct in the first place, and not just like do it 4 times to get every possible permutation of answer choice. That's not the intended consequence, but I realize that is one pathway to a perfect score. So I just want to roll through these very quickly. Imagine a friend wants to know how one quantitative variable relates linearly to another variable. So this is a bivariate question, introducing or reestablishing vocabulary. Bi meaning 2, we're going to see that again today as well. Which of the following strategies could they use to answer that question? So if you have a quantitative variable and you're only interested in a linear relationship with another quantitative variable, you could use a Pearson correlation for that, or a general linear model. The effect size R that comes out of that general linear model will be the same thing as the Pearson correlation. The difference is just whether the analysis is using standardized variables. In the case of a Pearson correlation, the variables are z-scored first, and then essentially you compute the slope for that z-score, or the unstandardized version. So it's just a question of scale, but the relationship will be of the same magnitude in terms of whichever scale you're looking at. So either of those would work for that. For binary, the situation is the same. So because in binary data there's only one possible difference between the 0 group and the 1 group, there's only a linear relationship that is logically possible of that difference with some kind of quantitative outcome. So same situation, either a Pearson correlation or a linear model will work for that. However, as foreshadowing, I hope at some point to teach a class on generalized models, and as part of that class you would learn that Pearson correlations are not ideal for binary variables, because the correlation is limited by the distribution of each of those variables. Only when the variables are both split 50-50 is the maximum possible correlation 1. Otherwise it's something less than 1. And there are other kinds of correlations that are more appropriate for binary or ordinal data that would come into play then. So just a note for future you that Pearson correlation is not the only game in town. For nominal then, same question. If I want to know how a nominal variable relates to a quantitative variable, why does this need to be only a general linear model, folks? I can blow it up a little bit if you need to. Who's feeling brave or talkative? Because we only need the slopes? Maybe. Question mark? I'll pronounce the question mark. I think you have it right, but can you tell me more about that? We only need the slopes.
We're only interested in knowing how they correlate together because we know that they go in order, maybe?
Well, if it's nominal, the categories are not necessarily ordered. But the multiple slopes is, I think, the key issue. So if I were to enter a nominal predictor, let's say that's coded 1, 2, 3, 4 for different groups, into a correlation analysis with a quantitative variable, would that make any kind of sense?
Can you ask that again,
I
please?
can try. So if I have a variable such as favorite ice cream flavor, and I have chocolate, vanilla, strawberry, or mint chip, clearly the incorrect answer is mint chip, but the others are, somewhere in the middle. But no matter what numbers I pick for those categories, they're not amounts, they're kinds. So if I try to treat it as a number, like how correlated is, ice cream type with a quantitative outcome, does that make any kind of sense? It does not. Will R or any other software package let you do it anyway? Yes. ChatGPT would love to help you with that kind of analysis, for instance. But it doesn't make a lot of sense. And the issue is that in order to talk about how the mean for the quantitative outcome differs across each of the potential categories, you have to divvy them up into binary contrasts of one category versus each of the others. That's at a minimum. If you have 4 categories, you'd need 3 slopes computed some way or another. And that's another question that folks wanted to talk about today, is just the idea of coding these different things. So because nominal variables aren't numbers, correlations don't make sense. So one of the requirements in your project is to examine the bivariate relationship of each of the predictors you care about with each of the outcomes you care about. So if you have a nominal predictor and a quantitative outcome, the only way to do that is a general linear model. And that would be the same type of thing you did at the beginning of homework 3 for the golf groups, for instance. You've got templates for that. We did that a couple different times in class. And I'm happy to point you towards specific examples too if needed, if you're like, did we do this? Because you may stumble into a category where we don't have an exact match, but I can always help you figure that out. Okay, does that make sense?
Mm-hmm.
Nominal and quantitative. Okay. Next question. Slightly higher level of difficulty. Your friend wants to know how one ordinal variable with 5 categories relates to a quantitative variable. And by the way, this your friend asks you thing is 100% legit. Welcome to my life. My friends are often academics, and we often end up talking shop, and they ask me questions, and I'm happy to try and help, and I ask them questions about their work, and they're happy to try and help. So this is not a fictional story. And you may find yourself becoming more popular with your friends or peers or otherwise as you develop these additional research skills. So if your friend wants to know how one ordinal variable with 5 categories relates to a quantitative variable, so something like strongly disagree, disagree, neutral, agree, strongly agree. Those types of scales are very common. Her advisor says, no, that's a number. It's close enough. It's fine. It's continue-ish. In which of the following scenarios would that be reasonable? So we've got a couple answer choices here. If the linear slope for the ordinal predictor is significant, was one choice selected, and if the outcome differences between adjacent categories were equivalent in size. So why does it need to be this one?
I think so that the distance between them is, I'm gonna mess this up, but I'm gonna say it as crudely as possible, as crudely as I have available to me discursively. The distance between them is equal, so it's like going from a 1 to a 2 and a 2 to a 3 and a 3 to a 4 and a 4 to a 5. It's like you can interpret that versus if there's large gaps between a 4 and a 5 and then small gaps between a 4 and a 3, you couldn't treat it as a quantitative variable because then it's like they're flattening them. I have no idea if I said that right, but
No, that sounds legit to me. Yeah, said very well. Um, Essentially, you're building a line, of these sequential differences, and if they fit the same line, then treating that as a linear relationship, essentially treating it as a number, is a reasonable thing to do. But yeah, if you go up, if you move from 1 to 2, but down if you go from 2 to 3, like it's still not a number, but then it's like you're not representing the relationships accurately if you don't have these equal distances, meaning equal changes in the outcome. So it's not so much a number versus not a number in this case, but whether a linear relationship is a plausible thing, and a linear relationship sort of is what's typically used for interval type data, but could be plausible for ordinal. So yes, I like your answer. Thank you.
So, Dr. Hoffman, I am the one person that got this one wrong. And it's because, like, exactly what you're describing. Like, I was thinking, like, if it's linear, and I may be thinking too elementary, but like, if it's linear, then it seems like there is a rise over run relationship, like where there is some kind of pattern, consistency, equal sizing, like what you're talking about. And like the example that you just gave, where like if it dips down at any point, then wouldn't it not be linear? So go for it.
No, go ahead. I was just getting paint out and getting ready to draw.
So like I can't think of a real life example, but I'm just thinking about numbers. So if I'm thinking about coordinate pairs basically, so that's why maybe I'm just like too elementary here, but like in order for it to be linear, doesn't there has to be a slope? Like it has to be consistently growing at some kind of rate.
Mm-hmm.
If it's not doing that, then it won't be linear.
So
So then why isn't the linear relationship being significant? Why isn't that the answer? Like I saw the answer as when it says like if a linear slope for the ordinal predictor is significant, as saying if it was linear, like if it created a line.
okay, let me draw a picture that I think might help. Let's say that there is a measure in which, let's go frequency this time. How often do you do this thing? Never, occasionally, sometimes, often, all the time, something like that. And let's say that the thing is something very bad for you, like abusing illicit drugs or something. How often do you do this, right? Never would be the ideal scenario in terms of folks' health, but there's variability. Let's say that this is an outcome that's bad for you. I'm just going to make a frowny face right here. Well, let's say if you go from never to occasionally, your outcomes are worse, but after that, it doesn't really matter. That could
Correct.
happen.
But then that's not a line, though. I feel like that's not a line.
Exactly. But if you pretended that these numbers are numbers, right? So we got our scale here at the bottom, here to the best of my mousing. Really got to get myself one of those pens. And you fit a linear relationship, it might look something like that. And so it could be significant in the sense that there is a trend. If you treat this as equal distances translate into the same distance in the outcome, but the line doesn't fit is the issue in that case. So this type of pattern, this like shelf pattern here that I tried to draw, that would never be apparent to you if you didn't actually look at what is the difference between 1 and 2, and 2 and 3, and 3 and 4, and 4 and 5. Does that help?
It does help. It helps when you said it doesn't it doesn't fit. So like it's not a true line, but if I'm summarizing, I guess, or looking like big picture, it might seem as if it's linear, but really it's this up and then flat line.
Yeah, and
That
there's
we're
other,
saying that it trends into a line, like it trends into a line, but it's not really linear.
yeah, and
And
you
it
can,
might trend into a significant linear line, but it's not a true line.
yeah, it's not a good enough line, is what I would say.
A
Like
good
it's
enough line.
not capturing the pattern. So think about like a pattern like this, like a trapezoid or something, right? So this change matters and this change matters, but the other ones don't. A best fit line through that would probably be flat. And then you'd come to the opposite conclusion that though there's no relationship here, but it's just because the line doesn't fit. Like it's not the right line yet.
I'm getting it makes a little bit more sense.
Okay, well, thank you for being brave enough to share your thought process in selecting this answer. Hugh, do you have a question?
I have a comment.
Okay, is it
I
a
don't
polite
really
comment?
Yeah, I don't really understand the stuff.
Yeah, that's okay, buddy. You're in fifth grade, and this stuff doesn't show up in your standards until actually next year. Sixth grade and seventh grade starts to do a little bit of this measures of central tendency, I think,
I
in
probably
graphing.
would, but I don't understand what any of the words means.
I understand, buddy, and I appreciate that you're trying.
Okay, thank you. I've been paying attention too, it's because I can't understand what the words have been saying.
I get that. There's a lot of terminology that's new.
Same here.
Hmm.
Same. I agree.
I was gonna say, buddy, you're not alone. We've been in this class. Sometimes we don't get it either. It's okay.
The important thing is to be willing to admit when you don't know something because that's the only way through it. Like if it feels comfortable and safe, you're doing it wrong. Like it should be, it should feel this way, like it's part of the process, even though that doesn't make it feel any better. Just knowing that it's typical, I think, is the important thing.
Yeah, I like it more when the work is easier
Yeah.
because, like, it feels easy so that way you can rush through it. Because a lot of the work I'm doing right now in my school is just kind of time consuming. It's like a bunch of tests to figure out where you are.
Yeah. Yeah. He had to
Like
do
iReady,
iReady.
if you know what that is.
They do know what that is. A lot of them do. Yeah.
Oh,
All right, Hugh.
wow.
So
Do they
we're
have
gonna
to
get
do
back to
that?
the plan, okay, buddy?
Okay, thank
Thank
you.
you.
Bye bye.
Okay. So yes, and in case you're wondering about his last name, we call our house Hoffman Estates in honor of him. Um, since I'm Hoffman and my husband is Templin, we thought about hyphenating, but Hoffman Templin sounded like a law firm, and we didn't like the vibe of that. So we decided to make him a new name, and so he is Hugh Hoffman. He was Huey up until a few years ago when he told me I wasn't allowed to call him that anymore. But I had a baby Huey for a number of years. But anywho, back to the program. Let's see here. Imagine you are predicting a quantitative outcome from a nominal predictor with 5 groups using indicator coding to capture the 4 needed binary variables. In the results, the p-values for the 4 individual predictor slopes are all non-significant. So it looks like the groups don't differ. But the model f-test is significant. So which of the following is not a correct conclusion? And I know the not is tricky, but I wanted to, again, work with synonyms and be like, here are multiple ways of describing what happened. What's not one of them? So I had a question from someone about my terminology here, and after looking back on it, I'm like, yep, that was a little sloppy, but also maybe intended because people use synonyms for things. So in this type of coding scheme, there is the reference group is sort of an accepted terminology for whoever 0 is across the board. And so then each of the slopes under indicator coding contrasts one of the other groups against that reference group. The other groups are sometimes called non-reference groups, and they're also sometimes called alternative groups. So those are meant to be synonyms. I sometimes hear the word focal group put in the mix, but it's used inconsistently to sometimes mean the reference and sometimes mean the not reference. So I tend not to use that one. Reference and alternative is what you'll hear me say most often, but non-reference is a synonym for alternative. So I apologize if that was unintendedly confusing. But the only situation that we can tell for sure then that's wrong is the reference group differs significantly from the alternative group because that's what the slopes in the model would have been capturing. And if they're not significant, then there's no differences of the reference group with each of those other groups. However, we're missing part of the story, right? Because if I have 5 groups, that is 10 possible comparisons. So I've got 4 in front of me that aren't significant. That means somewhere in the other 6, there's something going on. So this is something that showed up in our example last week, and that you may see in your project data as well. Just because these particular group differences are not significant doesn't mean that the others might not be as well. Like you have to sort of dig and find those things out. So does anyone have any questions or comments on this question? And okay, Carlos, I'm going to answer your question that you asked me on the formative assessment now, if that's all right. Okay. He's like, why do I have to code up these variables? Can I just use EM means and get all the means and the mean differences? The answer is yes, you can. The reason that we're doing it the manual way to start with is so that you understand the underlying model and the underlying concepts that EM means is using to generate these kind of combinations. In a situation in which you only have like one 5-group variable, it's probably overkill to go through this manual process. However, where we're headed in Unit 5 is interaction terms, meaning that the group differences would potentially interact with other predictors, either quantitative or categorical predictors. And then there are multiple sets of potential group differences you might be interested in. And knowing how the machinery works behind the scenes can be a little bit tricky, especially in R. So I've encountered situations in which I thought R should have been doing one thing and it turns out it was doing something else when you let it do the coding for you. So I tend to be a little gun shy on that. But I think we should have time in the last 2 classes for me to show you what it's like to use what's known as a factor variable, in which R or any other program makes those dummy codes for you. So that's one reason, is because I'm trying to teach you the underlying model representation that you can then extend as needed for different kinds of circumstances, different kinds of variables, and different kinds of analyses. Like these concepts show up in multi-level models, structural equation models, generalized models, like every other kind. Like this is a very core like level concept that I want you to have. The other thing is that when you ask the program to do the coding for you, you don't get choices. So it's going to pick your reference group for you. It's going to pick indicator coding. As far as I know, there's no way to make it do sequential coding or any other combination that might be more appropriate in certain circumstances. So to start with, I think it's useful to understand what the programs are doing for you behind the scenes. Once you understand that well enough to hack it, then you can use these simplification functions that will spit out all combinations of all the things. So does that help? It's slightly pedagogical, but also that's in reality what is sometimes needed.
Yes, it helped. I just was like, I did it once, and I was like, and I did it on a like separate project, not for the homework, and I was like, okay, it took me like 45 minutes to do this. Then I was like, oh, okay, I get, that. I think the hard part about it for me is the mapping of a 0 and 1 matrix in R in particular, when you can't, like, if I could like make a little table that has little rows and stuff like that, I could do that. But so I think it was just hard conceptually. I had to do a lot of playing around with like to make sure the order was right. So that's why at that point I was like, I wonder if there's a better way to do this.
There is a faster way for most things. The question is like, do you know what it's doing for you? Is always the thing. All right, let's see here. So in terms of unique effects, the next few questions. Imagine 3 variables are all related. You estimate a model with variable A in predicting C, and then you add B in predicting C. Which of the following is true? The slope of A will likely differ across models. When would that not occur? When would the effect of A in predicting C stay the same if A and B were both predicting C?
When B doesn't actually have any effect.
Yeah, that would be one. Not the one I was thinking of, but that would happen.
When they're completely uncorrelated, they're not like, if we were thinking about the Venn diagrams, they're not intersecting.
Yes, that's where my head went, is if A and B are unrelated to each other, then each unique contribution is the same as its bivariate contribution. Like each has its own lane, essentially, and it stays in its lane. It's when they're intersecting in the Venn diagram, when there's that shared overlap, then you're not entirely sure what you're going to get. It will be different, and I phrased it that way generically because usually the relationships are smaller after you control for other variables, but not necessarily always. If the predictors are negatively correlated, for instance, that can actually make it so they're stronger after controlling for each other. That's known as suppression. Can happen. Let's see. There's no guarantee, though, that the slope of A would be significant in either model necessarily without knowing whether it's related to C in the first place and whether it's uniquely related to C after controlling for B. So any questions on that one?
I think I get it. Is this where you were talking about the TV show? Like,
Yes. Yes, This Is Us. Hmm.
Yes, This Is Us. I love that show, by the way. I just couldn't think of the name. Um, that was my only question. I think it makes sense when I try to like think back to what you were saying. Like while you were saying it, it wasn't making sense. And even when I was answering, I was trying to the Venn diagram actually just helped when she said the Venn diagram. I just wanted to make sure that I was connecting the right dots.
Yep, the Venn diagram with the Pearsons. Yep. Yes, my Facebook feed now, because I had searched for This Is Us recently, is full of clips from the show. I'm gonna have to go back and rewatch it because right now I'm watching it in like 30-second increments. And like, at some point, you just have to give in, right? Give in to the algorithms. I did that already for Grey's Anatomy. I watched
You
the whole
can watch
thing.
Paradise. It
Oh,
has Randall in Paradise.
oh yeah, yeah. I have not seen the spinoffs. That's actually how people watch shows now. Yeah, but they're out of order.
But it's like a whole media thing around people being like, "Oh yeah, I rewatched Breaking Bad in 30-second segments." It's like, anyway.
Yeah. Well, like I said, I did that with like 22 seasons of Grey's Anatomy, and I've forgotten like how many things happened that you would not understand. Like, who are these people if you had just watched it in the 30-second increments? But, anywho. Okay, same scenario. So A predicts C, then A and B predict C with linear slopes. Which of the following will be true? A test of the change in the R-square after adding B is not needed because it will be equivalent to the test of the slope for B in the model. Yes. So the idea is that if you have stuff in a model and it generates this much R-square, and you add one thing, if that new one thing is significant, you know that the change in the R-square it created is significant. It's a one-to-one correspondence. It's only when you add multiple new things, such as cough, cough, 2 different GRE scores, that you would need a separate command to say what is the test of the 2 new slopes by themselves that generated that increase in R-square, and the f-test would be used for that because it's multiple slopes at the same time. Otherwise, if you just have one slope and you did that same model comparison process, the t that you get for that individual slope in the model, square it, and that will be your f for the change in the R-square. It's the same thing. Okay, yes, sorry for difficult wording, if need be. All right, any questions on model comparisons and when you need them? The short answer is when you add more than one thing. Okay, fair enough. Such as, yeah, last question. Imagine a researcher wishes to examine whether a set of demographic variables predict an outcome above and beyond scores on a cognitive test. So they start with a model with just the cognitive test and then they add 3 more things. How would the researcher know whether those 3 new things helped explain unique variance, the change in the R-square, and the corresponding f-test for that one, because it's 3 new things. So in your projects, the rubric recommends a simultaneous strategy when possible, but if you have hypotheses of, does this contribute above and beyond something else, one could make an argument for sequential models like this where you're adding things in layers. The only catch is that the stuff that's get added first, that contribution at that step is not going to be the same as the ending contribution it makes after all the other competitors are involved. So you have to be careful in what you make for an inference about how much something matters. It matters above and beyond what's already there, but as you add stuff, like that's a higher bar to clear above and beyond. Semi-partial and partial R was the last one. A couple of folks asked about this. So what's the difference? Let me just review before we get into the question. What's the difference between partial and semi-partial? It's been 2 whole weeks.
Semi-partial is the part of the pie that's left.
That's right.
Backwards.
Partial
Okay.
is what of what's left. And semi-partial is of all of it. So it's exactly backwards as what you might think based on the words. Because to me, semi-partial implies of what's left, but that's not what it means. A synonym for semi-partial, by the way, is part. So sometimes you hear part and partial, which is also a phrase, I think, but it's a different partial, part and parcel. Yeah, I don't know what that means either, but at some point the words just stop making any sense because they're too similar. But yes, so semi-partial then. is out of the total. So how much of the R square is this predictor responsible for? That's semi-partial. Partial is of what's left, that the other predictors, like they already did their work, of what's left, how much is this predictor responsible for? That is partial R square. And to me, that is less useful because people want to talk about it as a contribution to R square, but that's not what it means. The model R square is not part of the story. It's only part of the story when you're talking about semi-partial. So which of the following is correct about semi-partial for 3 slopes from a 4-group predictor? It indicates the unique contribution to the model R square for the overall effective group. Yes. By the way, overall, a synonym for that you will hear in this context is omnibus. The omnibus effective group is a NOVA language for what you get when you're lumping the set of slopes together for a hypothesis test about the overall effective group, because that controls not just the 3 differences that are given directly by the model, but all the differences that are implied across those categories. This one, what is this one talking about? It indicates the proportion of variance accounted for by group that the other slopes in the model didn't already explain. Is that partial or semi-partial? This one is regular partial. Semi is of the total. So the caveat at the end here, that the other slopes in the model didn't already explain, was meant to differentiate those two. So yeah, this is a partial interpretation instead of semi-partial. And then one last real question, and then I'll make sure we hit everything that's on the list here. Which of the following is not a consequence of increasing sample size? The correct answer, larger effect sizes. You don't have a lot of control over that. You can't just get more people and change the strength of a relationship. But what does change is the precision of the relationship. So in every case, standard errors shrink. The idea is that what you get in any one sample is less noisy across repeated samples the more people you have in that sample. So I don't know if you remember this from a couple, months ago. The little histogram plots that got squished in when there were more people. It's that concept. Carlos, did I see you unmute yourself? Did you have a question?
Yeah, I wanted to check my thing. I think I got this wrong, and I think I picked smaller standard errors only because I felt like I actually don't know which all of these are. I think in my head, what I was thinking here was, and I think this is actually greater statistical power, but I want to check my thinking. I think when I was thinking larger, when I read larger effect sizes, I read the ability to detect effect sizes, and that's actually greater statistical power. Is that right?
That's correct.
Okay,
Yep.
That's right. Thank you.
Yep, power is the probability of finding an effect of that size that if it's really there. And being able to reject the null for that specific effect size. So yep. So yeah, in the standard error formulas, n is in the denominator. So that means that the more people you get, the smaller the standard error. And p-values shows up because you have your estimate for whatever the slope or the difference is divided by the standard error. And the smaller the standard error is, the larger that ratio, your test statistic for t would be, and thus the smaller your p would be. So smaller standard errors lead to smaller p-values, which leads to greater statistical power for the same effect. But you can't control how large the effect is in absolute magnitude by just adding more people. All right. Let me get to, let's see, where did the Unit 4 review topics. I pasted all of these in here. Let's see, R square and its effects, unique effect sizes in semi-partial R square, and scenarios in which semi-R square and partial would be used. So all of those are separate comments that all kind of going on the same theme. Unique effect sizes is the partial family, in the sense of if you want to get an effect size for a slope, you can convert that t test statistic for the slope into a d or a partial r. You can also convert it into a semi-partial r if you have the model R square with you. But the way that people often want to talk about slopes is what this variable brings to the prediction above and beyond all the others. That's partial. But if you want to be able to say which predictor is most important, like which one has the largest contribution, then semi-partial would be the way to go on that, because then they're all on the same level playing field in terms of what it's out of the total, not just out of what's left, because what's left shifts as a function of which slope you're talking about, because then you're controlling for each of the others. So in practice, what I like to do is sort of split the difference. I would report partial family effect sizes for each of the individual slope parameters, but then I would also report the semi-partial R-square for each conceptual predictor. So like group, for instance, if it takes 4 slopes to make group, I would report a test of those 4 slopes together and how much the semi-partial R-square was from those 4 slopes as a set. Yeah, I think that's what I wanted to say about that. Does that help at all? I don't know if it does. Can someone think of an example from your work or your research where you would have a question as to what to use? I can think of one from mine, but I don't know if it's going to help or not. I could try. That's always worth a try, right? So in quantitative methods research, a lot of what we do is simulation based, where we make up data where we know what the right answers are. And then we do like 1,000 replications essentially under different conditions to see if we get the right answers back. In those kinds of studies, we would manipulate certain features of the data on purpose, like does it still work if your sample size is too small? Does it still work if you have low reliability for your predictors, that kind of thing? So we would have different conditions that we would deliberately introduce into the design to see what happens to the accuracy of our results under those different conditions. In those situations, I tend to report partial R-squares because then the inference is that condition relative to that condition plus error, where error in that case is across replications that are of the exact same kind in terms of how they were built, like the same sample size, same reliability, same whatever. And that quantifies the expected variability that you would get across like the same situation. And then you can compare how much more variability was introduced by your manipulation relative to what is just expected. And so the expected is conveyed by the residual term specifically that the partial R-square would be based on. The total R-square is less important because we did these manipulations on purpose. We're trying to see how they compare to what would be like the standard going rate in terms of the variability in the data without trying to introduce additional sources of it. So that's one situation in which I would prefer partial, but I realize that's not likely to be as relevant to you folks at this point. Not yet, anyway. Okay, so folks who ask for these topics, what else can I talk about or point you towards that might help you? Hugh, you don't have any questions?
Nope.
Nope. Okay. Well, thanks for...
It's challenging for me to have questions. I didn't really do any of the work because I just got here, so like I don't need any questions.
Yeah.
I've been looking for my chance to put the 3 dots up there because I know you like the 3 dots based on some stories I write.
Yes, ellipses. I'm a fan of ellipses.
And so every single time you ask that question, it's just been a break. I was trying to type in, and then while I was typing, it's on the answer. And now that no one's answering, I finally got to say it. So, bye-bye.
Okay, bye-bye. This is like grad school, try before you buy. When his age, I did not even know grad school was a thing. I didn't. It wasn't until I got to be a psychology major and they told us, like, in our Welcome to Psychology intro orientation course, hey, guess what? You're not getting a job unless you go to grad school. Okay, well, what's grad school? I guess I got to learn how to do that now. So I'm from a family where no one has gone to grad school, so that was a very new concept. Anywho.
I have I'm not sure. I think I want to there's something about the semi R squared and partial R squared that I think to this comment around using examples from the education field that I would like to play through. And I'm just gonna come up with like a classic one. Maybe some we have some measure. I'm just gonna use math proficiency, and I think two common conceptual variables, I guess, are like, let's just say I don't like using the word teaching quality, but I'm going to go ahead and just use some measure of teaching quality and some measure of the quality of curriculum. And we've like regressed math proficiency on teaching quality and on curriculum quality.
Okay.
The partial, and I'm going to let, and the main predictor is, let's say, teaching quality, some measure of teaching quality. The partial R squared is the contribution of teaching quality when I don't even feel comfortable in saying this. I'm going to say it, and then if it's wrong, it's fine. The contribution of teaching quality to math proficiency when accounting for no, I don't even like how I'm saying this. I'm struggling. I think the problem is I'm like trying to think about the Venn diagram, and there is some contribution that teaching quality has that is unique to teaching quality, and that is semi-partial. And then the total contribution of teaching quality when also including the relationship between teaching quality and curriculum quality.
Okay, let me try to help.
Okay.
Let me do this two ways. We'll do the R square way, and then we'll do the R way. So the R square way is semi-partial would be, what is the contribution of teaching quality in predicting this? Like, period. And that size of the contribution will depend on what else is in the model, but the denominator is all the variance in math proficiency rates, or whatever your math outcome is. And then the partial would be, of the variability in math that's unrelated to teacher quality, how much did curriculum quality get? So it's both of them are controlling for other things, but the question is, what is the denominator? In semi-partial, it's total variance. In partial, it's that thing plus the residual variance. So it's scaled relative to just the error part of the model, not relative to the whole thing. I like semi-partial when you're talking about R squares, because you can say, like, if the model R square in predicting proficiency was 0.2 and teacher quality was 0.15, then you can say of like the 20%, like 15%, that much of it, not a proportion, but that much of it is due to this variable, and that means this other variable had some other lower amount because they're going to be correlated. If you want to talk about it as correlations instead, then you can think about, in the R version, semi-partial is controlling the predictor for its relationship with the other predictors, but not controlling the outcome. Partial is controlling that predictor for the other predictors and the outcome for the other predictors. It's like the leftover parts of each variable are being correlated in partial, but it's the leftover part of X and the total part of Y in semi-partial. Like, it's like, nope, not worse. I mean, not better, we're making it worse. Oh, I'm trying. Yeah, I like semi-partials better if you're talking about the contribution of a variable to the model, but if you're talking about like that individual slope, then partial, I think, is an acceptable version of that as well.
I have an idea, but I'm not sure if it's going to work or not.
Okay.
So I have my students in pre-cal, for example. I have students who I teach juniors and seniors. So I got students who got 90s, and both juniors and seniors. And then the seniors can exempt my final. And I can calculate how much in total, all of them, the ones who get the 90s, that will be, like, I'm thinking about how much that contributes to the overall grade when I have all of them. And when the seniors exempt, and then I do the testing again, and the partial would be for the juniors that are affecting the grade, because I no longer have the seniors to. So I accounted for the seniors that get 90s and above. I removed that. So the partial will be for the juniors who contribute to the average. Does that work?
I think it might work the other way, at least in the way I'm thinking about it. Like if you want to know how much does the test, how much does the rest of the work contribute to their overall grade, like versus how much does it contribute to the grade minus their final. Grade minus their final, I think, would be the partial version, versus overall grade is the semi-partial.
Okay.
I
I still
think.
have to wrap my head around the semi and the partial correctly.
Yeah,
I know it with the Venn diagrams. I just don't know how to do it again in other ways.
There is, I'm pretty sure I put an article on your reading list about this because it is not easy to follow. It's just not. Yeah, so Lakin's 2013, there's a tutorial about effect sizes, and he talks about also what programs do and why it's misunderstood. So yeah, calculating and reporting effect sizes to facilitate cumulative science. I would recommend taking a look at that article because I feel like I'm not doing a great job on this topic. So I'm gonna call an audible and phone a friend. And this guy's gonna take off where I failed. These articles, by the way, are for your future selves, but if there's stuff that you're like, this makes zero sense to me, can I hear it a different way? I would encourage you to go to these other sources because we all have our own way of explaining things, and sometimes different ways resonate better with folks than others. All right, let me get back to my list here. Okay, so are we good for now with partial and semi-partial? As good as it's going to get for today? Maybe not done, but just done enough. Okay, we'll keep working on it. Let's see, we clarified the wording on these things. Dummy coding and interpretation patterns in GLM and ANOVA. And then the rest of this we talked about. So for this one, is it when is it 1 and minus 1? And when is it 0 and 1? That kind of thing? Because we can talk about that. Let me open up a spreadsheet here. This is the way that I always think about things. So if we have group and we have A, B, C, and D. Under indicator coding, who do you want to be the reference for this fake example? Pick a letter. Me. I don't have a group H, sweetheart. Can you pick another letter? A. Okay, well that'll work just fine then. So that means if I want A to be my reference, first step, I zero out the 3 columns that I'm making. Now, if I want to do indicator coding, if I want this first variable to represent A versus B, what goes here? 01, very good. What goes here? A 0, a 0. Okay. Then the next one over would be A versus C under this system, A versus D. Nope. There we go. And I know this typing is very loud next to my thing. I apologize for that. I'm trying to type quietly. What goes here? 0. What goes here? 1. And what goes here? Okay, we got this one. So if you use a factor variable in R, that's what it's doing for you. It's creating these columns. Oh, there we go. So then there's a 1 and only 1 spot for each one, which means that that category is compared back to the reference. That this is not the only game in town. What if I wanted to do sequential coding? So I wanted to know about A versus B, and then I wanted to know about B versus C, and then I wanted to know about C versus D. How does this have to change? Such as in homework 4.
You've got to put everything before the last one that you're looking at has to be ones because they're already accounted for,
Yeah.
right?
Yep. Basically, it changes to that. Yep. So these patterns then have implications for how you would build a prediction. So let me look at this one. What if I wanted A versus D? Can the model get that to me somehow? Yes, it can, Hugh, but not directly. But we can work our way there, because if this one gives me A versus B, so that would be like, let's go beta, we're going to abbreviate the slopes like this here. So this would be beta 1 for this variable, beta 2, beta 3. And if B versus C gives me this one, then I just need to get from C to D. So it's like a ladder. So those three differences grouped together would get me all the way from A up to D. So the trick to any of these coding schemes is first working out in your head, like, how is the mean for that group built? And then you can compute the mean differences relative to each of those means however you want. So this one then, this coding scheme would require all three slopes to be lumped together if it's using this sequential process. Whereas if we didn't do that, then A versus D would just be this column right here, all by itself.
Sorry, I'm having a hard time understanding. Maybe it's just because it's a little bit more abstract. How A versus B gets C and D get coded as 1.
Okay, let me stop switching back and forth and label these things properly. How about that? So this is indicator coding.
Yes.
Right now I've got like a hodgepodge of both here. Come on. Okay, so this one is now sequential. Put them back. That means that the labels for these three need to change back to what they were as well. That one actually is the same. Okay, so if I want A versus D, I get that directly right here in an indicator coding scheme, because it's whatever your reference group is relative to each other group as a separate entity.
Yes.
So if I have, let me put the labels of the slopes up here. Okay, so then down here, if I wanted to know, say, C versus D, I can start with, what is the model for C? It's beta 0. Nope. 1 second. Okay, so building the two means that the model is trying to recreate. Then if I wanted to know C versus D, it would be D minus C computed here, so the beta zeros drop, and it would be beta 3 minus beta 1. So in the R command, like the values you would fill in would be 0 for beta 0, 0 for beta 1, -1 for beta 2, and 1 for beta 3. And question in the chat, is it still a linear combination when it is not sequential? The slopes would be 0. It's a linear combination anytime you have to add or subtract multiple quantities to get a new one. Otherwise, you're not combining anything. But there's lots and lots of kinds of that in instances in which you would want to do that. So in this case, it would look like this. If I wanted to do over here for sequential coding, because each of these only gets me so far, I would have to add together the 3 slopes. So in terms of what it would look like in R, it would be like this. And that creates the difference, because each of these differences is like one part of the way there under this scheme. So the way you set it up entirely dictates how you find the differences. But the process is the same. Basically, you would compute what does the model say the mean's going to be for each variable, and then you can use those means to literally subtract between them to get to whatever implied mean difference you want to have. Let's do A versus C. What would that one be? Is a slope a triangle? It's one of the lines on the triangle, buddy.
Oh.
What would A versus
So
C
like-
need to be? Beta 1 plus beta 2, ding, ding, ding. Yep, you just need to get like that far. Can I show you yet another kind? So let's say that you're studying a pattern in which you have a majority group, and then you have 2 different kinds of minority groups, something like that. Which of the 2 coding schemes do you think would be more useful for this? It's a trick question because neither of them is the answer. So if I did indicator coding, I could make majority the reference, and I would get slopes that tell me how minority 1 differs from majority or how minority 2 differs from majority. But neither of those gives me like, what is the effect of being a minority period, for instance. Like we might want to know that as a comparison. So we could do something like this. So if I made the majority the reference, like this, I might do something like that for the first one. So I'm explicitly lumping together the 2 different groups that are considered minorities, so I can ask the question, if you're a part of a minority group, how different is your outcome than if you're part of a majority group? So far, so good. Over here, I might do something like this. So when these are both in the model, this first contrast differentiates this one from both of these combined. The second one then just differentiates among the 2 kinds. So if you're part of a minority group, does it matter which one? So this kind of coding scheme, I don't know what it would be called, but this is a way in which you can sort of further break apart groups in whatever way is most relevant to you. And if it turns out that kind doesn't matter for your analysis, that there is no difference, you could just retain this version of the variable in which they're lumped together explicitly, and that would create a more parsimonious or less complicated model.
What is this type of coding called again?
I don't know the answer to that. In your textbook, though, there's like 2 pages of different coding schemes that they use in these tables, and I think it has a name, I just don't know what it is. But note that I'm using plus or minus 0.5 so that the slope still refers to a unit difference and not plus or minus 1, in which it's 2 units, and the slope would be twice what it should be.
Does it matter which one gets the negative sign?
Nope. Nope, that just controls the interpretation of the slope as to who's higher. So this is another example. There's lots. There's lots of different coding schemes. And it doesn't matter in the sense that the end of the result is the same, but it does matter in the sense that when you start building more complicated models, like having interaction terms, which is what we're heading towards, that the model parameters you want are direct as much as possible. It takes more work to get different predictions that are implied by the model than what's been given directly. So if this is what I want to know, is there an effect of being a minority, and is there a different effect of being this kind versus that kind? This coding scheme directly answers that question. Whereas like indicator coding would give me majority versus each other. It doesn't directly answer the first question. And minority 1 versus 2 would be a linear combination I have to keep asking for to do different things with. Let me blow your mind another way. Back to this. What if you just want to know what the group mean is for each one? What if I did something like this? This is yet another alternative. Now, you haven't seen something like this yet, for good reason. If I tried to put all 3 of these variables in the analysis at the same time, what would happen? Want to take a guess?
It would assume that they're all equal and how they affect. But we said the majority has more, right?
The majority group could have more folks. It doesn't actually change the storyline for this. This would differentiate the groups, but would you get all 3 of these contrasts back? What's the rule? If I have C categories for the number of groups that I'm trying to pull apart, how many slopes do I need?
2.
I need 2. I've got 3. So if you tried to feed this into R, it would kick out one of them. I'm not sure which one it would kick out. Either the first or the last would be my guess. But this could work if you removed the fixed intercept from the model. If I did that, these change interpretations. They're no longer differences, they're means. Because without the fixed intercept as like the starting point to add things to, this variable would give me directly the mean for the majority group. This would give me directly the mean for this group and the mean for this group. So you can ask your model to directly create means rather than mean differences if you want to. And I have done that in certain situations where the design was sufficiently complex that I was never going to be able to figure out all the differences, and so I just put them in the model as means like this. And then any group difference you want is a linear combination across these 3 variables. So that's an alternative. I tend to do it this way if I'm fitting multivariate models in which I want to create a separate equation for each outcome. I will give each equation like its own custom intercept with these sorts of switches. So we'll see this at the very end of lecture 5 as well, special cases with nested effects. So the point of the story is there's a lot of choices. In some situations, the computer can make some choices for you, but you have to know what the choices are and whether you want those choices to be part of your model. There's a lot of non-traditional designs in which alternative strategies like these could be more useful to you potentially. All right. Questions, comments?
I have a quick question sort of about this. So I can't remember if you said it in one of the videos, if I read it in the rubric, but you suggested starting with everything as a full model, like when we're doing research, and then take things out.
Mm-hmm.
Is that how you want us to do our project?
So I can pull that up if that would be helpful.
Okay. I mean, I was just thinking like starting with everything and then pulling stuff out is going to be a little trickier for my brain because it's this class is tricky anyway, and I've learned one way and now I got to go backwards.
So what I'm asking for each folks under results is basically 2 different sets of results, bivariate relations and unique relations. The reason for that is I would like for you to be able to tell me, are these 2 variables related, period? And are they still related after you factor in all the other stuff you care about? because those are two different questions. How to get there, I'm willing to give you a little bit of leeway. But yes, in general, I think a safer strategy is to start with everything you care about in the model and simplify. Because then there's no question as to whether you would have landed at the same place if you had went through a different order. So where you can get into trouble is like, I'm going to add predictor A. Oh, it's not significant. I'm going to take it out. Now I'm going to add predictor B. I'm going to keep it. Now I'm going to add C. I'm going to keep it. But you could have reintroduced A in the third step, and it actually could be significant even though it wasn't in the first step, because there's less residual variance that goes into its standard error, so its slope would look more precise if the model is better than if the model is worse. So that can happen if you add things sequentially, but it can also happen the other way to where the contribution of A would not be significant at the last step, even if it was at the first step, because of what it's competing against at the last step, it wasn't competing against at the first step. So to avoid that kind of like, what's the word I want? Choose your own adventure, like ambiguity, where you could have all these different pathways that are created, like having everything at once and then taking out what you don't need at that point seems like it would be a safer process. Now, the taking out part. Let's say that you have a quantitative predictor. It looks like it needs a linear slope and a quadratic slope. Once you put everything together, it looks like the quadratic slope isn't needed. I would go ahead and remove it because it's just going to complicate things unnecessarily. However, if you had a research question that said this relationship is not linear, then leaving the quadratic slope in to test that and report about it is the answer to the question. I would leave it in to make the point that, oh yeah, it looks like it was linear, it looks like it was nonlinear to start with, but now that nonlinearity has gone away since I've introduced other things. So like if the answer to the question is no, it doesn't matter, I feel like leaving the thing in to make that point is useful. Okay, did I make it worse?
No, I think it explains it. It's just trying to kind of wrap my brain around that whole concept. I mean, it makes sense. It makes perfect sense, but I have to figure out where the pieces go in my mind to make it work.
Yeah, like you might just build yourself like an outline, honestly, of like, I need to run this, and just like make sure you've got like all the steps.
Yeah.
Because figuring that part out is, I think, more difficult than just adapting the code at this
Right.
stage. Yep.
Yeah, that's kind of where my brain is. I'm like, oh, and I think I answered my own question about homework.
Okay.
I forgot to run R2 compare, right?
Okay. Yep.
Yeah.
Yep. And that is, so there's a function, that is my function that steals someone else's function and like customizes it for our purposes. So I think it's LM hierarchical or something like that is the package that it pulls from. At the start of the functions file are the packages that it uses particularly. So you can see those as well. But yeah, like this thing, as you can see, most of the points are towards the results, but I also have like the other pieces that you would need to start getting used to writing about in terms of just your method section, your research questions, that kind of thing. So yeah, I think that was, yep. I think we made it through the list. Don't need that for a moment. How about we take a break? Break time sound good? And then we can transition into lecture 5. Yep, okay, he wants a break. You really don't have to be here, buddy. Everyone else is contractually obligated to be here but you. All right, let's go with like 6:07 then. I'll see you in a bit.